Yep. Okay, so I got the recorder started. Although I'm not really sure which mic it's using. Let me double check. It's using the right mic. Okay, very good. All right, so we're going to get started. Um, not with FFmpeg, unless you guys want to know what it is and what to do with it. It's just one of those Linux command line tools. Um, I really have no idea why people are not showing up yet. Is today any special? I mean,
Live.
I I do not know what. Yeah. Okay. So what we are going to do today is to follow the plan in the announcements. And that's why I made the announcement because it's actually more like a note to self, of what I want to talk about today. All right. So we have an instruction called LDI in order, to explain. It's going to be part of the lab today. So this is going to be relevant to what we do today. I will continue to show you how to use the assembler, particularly how to use labels, how to define labels, how to reference labels, and also the use of byte in the assembler. So this is kind of the outline of what I'll be talking about today. So the first thing is to look into LDI. The first thing you want to go to take a look at if you want to learn about a new instruction is to go to the opcode table. So in the opcode table, you can do a control F to search for LDI, and that makes it very easy to find anything inside the spreadsheet. So control F works regardless of the browser because it is not a browser feature, it is actually a feature of Google Sheet. So now we take a look at LDI. So we're going to take a look of the entire row and find out what it is and how we use it. So let's look at column D first. So column D is actually is the easiest part to read for this particular opcode, and it says load constant value right after the opcode. So if you look at the actual format of the mnemonic in this case, it is LDI, and then X specifies one of the four registers, and then I is what we call an immediate value. From your perspective, an immediate value is simply an expression that evaluates to a constant. Is that okay? So when you see a lowercase I as one of the operands, this is the mnemonic of the instruction itself. So what is next to it are the operands. They're kind of like parameters of a function. So if you look at the operands, x always represents x and y represent registers, and then I represents a particular constant value. So I can give it. Yeah, go
You're
ahead.
just saying like in the diagram, there's some pin that's just constantly a single
Nope,
value.
not quite. So this is what the instruction looks like, but the way it works is a little bit more complex, and that's why I'm going to show you how this particular one works. Okay? So how it is done is demonstrated by column C. So column C is what we call the RTL description, or register transfer language description of how the operation is done. So in this case, there are a few alternatives. So let me go ahead and highlight the first one first. Okay, so this is personally, I think this is my favorite. This is this is my way. Okay, if I can choose just one way to represent what the instruction does, this is what it does. Um, it is asterisk, which is the reference, and then in parentheses PC++, which is a post increment, and then whatever the right hand side is, we copy that to a register X. So this is the best way to describe it, and you go like, but where's I? Well, I is actually implicitly what the program counter is pointing to at that moment. Okay? So we'll get to that. Okay, when I actually run the command inside the processor, it will actually be very clear of why it is represented like this. At the same time, for those people who do not want to know about the program counter or how RAM is accessed, in the process, this is the best way to describe it, which is simply whatever constant is put here is going to be copied to register X. Is that okay? So let me do a quick demonstration and then followed by a edge by edge explanation of how it happens. Yes, go ahead.
So that's that x equals I. It's not that they're equal to each other. It's that we're like programming language where we're assigning whatever the value of I
It
is
is
to
a
that.
single equal, which means it is an assignment operation.
Mhm.
So that means we evaluate the right hand side and then we copy the value of the right hand side to the left hand side. Yep, so you're correct. It's good to double check because in certain programming languages, single equal can be comparison and also assignment. Fortunately in C, well, fortunately and unfortunately in C and C++, equal is assignment, double equal is comparison. Okay. All right. So with that said, I'm going to go to my assembler. You do not need to go here because the program is really simple. And we go to source, and then we go ahead and take a look at this example. I don't need the increment here. Instead, I'll put a line of comment here and say, register A should have a value of 36 at this point. So the comment is the same as C, C++. If you start a line or anywhere to the right-hand side of the slash slash, is ignored by the assembler. Are we good so far? Okay. So the first thing, okay, so I'm not gonna explain the detail. So I'll go straight to the RAM file that looks like this. Okay, I think I can just hand copy everything over, 6C24 and the 01. And I do have Logisim running already. Let me just kind of copy or move that over to this side. And where's my cursor? There we go. There we go. So now we get to the RAM and okay, let me just kind of show you guys how to download the file and then put it back into the assembler. I have done that a few times already, but it doesn't hurt to do it one more time. So the key is go to the RAM file tab, and then you go to File, and then you go to Download CSV. And my browser is set up so that it prompts me, where I want to save, where I want to save the file to. I would advise you to do the same because it is actually quite useful when you have control over where you're saving the file to. Do you guys know how to configure your browser to do the same, more or less? You can probably Google search. Okay, you can Google search. In my case, you can go to, this is Firefox. You can go to the hamburger thing, to do the config, and then go to settings. And if you scroll down, um, where is it? It's There we go. So under files and applications, I just check this mark here, which is always ask you where to save files. So this works in Firefox. Chrome probably describes it a little bit differently, but it has similar settings in Chrome as well. All right, so I do have the file already downloaded. So now I can switch back to Logisim and right click on the RAM component. So remember, do not load this into the ROM because it's going to kill the ROM and then the processor won't work anymore. So we say load image, and then it is in my temp folder. It's called test.csv. Click open, and the file is now here. So I'm going to do a very quick run, okay, because I want to show you the end result of running that particular instruction, and then I'll give you a much more detailed explanation of how it happens. So I want to confirm that register A is now a 00. It is not not what the program wants to, change it to. So I just want to make that clear, and then go back to main. And if you really don't care about how it happens, and you just want to get as quickly as possible to the end of the whole thing, the quickest way to do it is to go to simulate. Make sure your tick frequency is maxed out at 4.1 kilohertz, and then just enable ticking. You can also type Control K to start the ticking, like so. And the way we know that we are at the end of the execution of a program, there are two ways you can tell. One is the program counter does not change. Okay, I lied. There are three ways to tell. The program counter is not moving. The microcode pointer is also not moving. And the halt pin is a 1. So any one of these three is indicative that your program has now finished. So we can now type Control K, stop the ticking, and then go back to the register bank and check on the value of register A right here, right click, go to view reg bank, and it is 24, which is correct because in decimal it was 36. 36 is 32 plus 4, and then 32 is 2 times 16. That's what the 2 is for. It means here we have two 16s, and then the 4 means we have four ones. So the way we perform base conversion has not changed, even though this is a base 16 number. It's just that the base is now 16 instead of 10 or 2 or 5 or 7. So are we doing okay so far with this particular opcode? Let me go back to the program to show you what the opcode looks like again, because that part is important. Oh, I just I just got past the the program. So this is the program. LDIA with 36 simply means load register A with a constant of 36. Are we good so far about the effect of the instruction? So now the question is, how does it get it done? Okay, because one of the biggest thing about this class, the way I teach this class, is I want to explain how it gets things done. Because this class is not just about assembly language programming, it is also about computer organization, which is what is inside the process and what makes it possible. Why does it get the job done, or how it gets the job done? So the next thing we want to look at is the assemble tab. The assemble tab is really quite useful because what it shows you is x1. Okay, I don't want to move this over because otherwise it shows the comment of the entire column. So you can see the 6C. The 6C is the actual opcode. And then what about the 2.4? What do you think this 2.4? Why do you think it is here? It's the 36, right? It is the value that we want to copy to register A. So that takes up the second byte of the instruction. Is that okay? All right. All right. So with that in mind, now I go back to Logisim and I'm going to run the program again. Oh, since I'm in Logisim, I want to kind of tell you guys the same thing that I told the class on Tuesday and Thursday. At this point of time, to study is kind of difficult because I can write everything down, in words, just like all the other modules, but it's going to be very difficult to follow because the whole thing is visual to begin with. So it's more difficult to kind of just write down, the visual thing, have screenshots, all over the place, and then just a few words in between. So you probably need to find a way for you to take notes. Okay, so I do not know what is the best way for you to take notes. One recommendation, one possible way, I'm not sure how well that's going to work for different people, is to create a PDF. I talked about this already in the past, but today I want to show you what it's going to look like when you use this approach. So you want to print to a PDF printer, and I know this works for all platforms. So just print, okay, so now I have that file, and let me show the Zerno screen at this point. Okay, so this will give, I was still working on the tool to get this done. So that's why I didn't have it working before. And one more command. Like so. Okay. So today I'm using Zerno++. Okay, let me move it here, which is Zerno, except it's rewritten in C++, and that's why it's called Zerno++. Um, okay, are you guys getting the funny part of this? Okay. All right. So Zerno is kind of neat because you can use it with a tablet, So if you have a tablet, it works. Otherwise, it will also work in, without the tablet, without a um, stylus. Okay, with a stylus, it's kind of like paper. Without, it would still be usable. So what we'll do is we are going to open. You cannot see the screen, but I can show you here. So we're going to open the PDF file that we just generated. So that's going to be this one, and you can see how the processor is over here. So one thing you can do, oh, okay, I'm scrolling in the wrong window. So one thing you can possibly do is to highlight it, okay? So for every single instruction, you want to basically highlight what path is being built as the instruction executes, okay? So I will be highlighting this along the way as I execute the instruction. So I have to go back to Logisim for now because I want to execute the instruction. We are currently going to, oh, okay, so there are a few things. One is to reset simulation, and, oh, okay, I should not have loaded the RAM component first. So I'm gonna load RAM image again, like that. Okay, so now we are ready to start the execution of the program. This is also something that I would like you guys to do at least once or twice, um, is to kind of follow, along, how things are done. We always start with the ROM, okay? We always start with the ROM, particularly the output of the ROM, which is this particular node here. Um, by itself, it's not really super useful, but then we can go up and find out, okay, how is it going to do everything? By the way, this is the fetch cycle. When the ROM, when the microcode pointer is at 0, 0, 0, and we're having a rising edge, this is called the fetch cycle. The fetch cycle is significant because this is how, or this is when we grab a byte from RAM and put it into a register, put it into the instruction register, so that we can know, so that the processor knows what am I supposed to do now. Okay, so it has a significance. It's called the fetch cycle. I'm not going to get into details of the fetch cycle because that was discussed last. No, it was just discussed on Monday, I believe. So it was already discussed on Monday. So we know the end result of the fetch cycle is the instruction register is going to grab the opcode that is pointed to by the program counter at this point. Are we good so far? Okay. Let me give you a description of the fetch cycle. So this way, if you choose to, you can put it in your own notes. But this is just a way to represent the fetch cycle. All right, so if we look into the fetch cycle, the microcode pointer has a value of 0, 0, 0. And I'll emphasize this is in hexadecimal. It's not super important, but it's important. Um, and then we have a rising edge, right? Rising edge. And then the effect is this, okay? The effect is the instruction register is going to get whatever the program counter is pointing to. Are we doing okay so far with this notation? When it happens, and what is the effect of the fetch cycle? Okay. All right, so with that done, I'm switching back to Logisim so that we can continue the simulation. So we're going to have a rising edge right now, so we can observe how the instruction register is getting the opcode, which is currently already pointed to by the program counter. So we can see, we should see how 6C would end up in the instruction register, which is right here. So here's Control T. Oh, okay, one more time. Control T, there we go. So the instruction register now has 6C, and then now we have a falling edge. This particular falling edge is not super exciting because the microcode pointer is simply going to increment at this point. So Control T, we can see the microcode pointer increments to 0, 0, 1. So we are ready to do something else with the rest of the processor. This part here is also not very exciting because the only thing that's going to happen in this step is the program counter gets auto incremented. It will increment from 0, 0 0, 1. So by itself, it's not very exciting, but it's important to understand why we want to increment the program counter. The reason why we want to increment the program counter is where the program counter is pointing to, which is the opcode that I need to use to figure out what I'm supposed to do next. I don't need to point to that location anymore because that byte, that opcode, is already stored in the instruction register. I don't need the program counter to keep pointing to the same location. Is that okay? So the program counter can now advance to the next location. So I'll be ready to take on the next opcode or whatever is next to it. Is that okay? Which is now also important, okay? I need to point this out. Also important is guess what is 0, 1, what is at location 0, 1? What is at location 0, 1 is 2, 4, which is the value that we want to store into register A. So the program counter is already pointing to the location that contains the value that I want to copy to register A. But it's not doing anything with it, okay? It's just going like, yep, I'm pointing over there, but it's not doing anything with it yet at this point. Alrighty, so now we just kind of move on. You'll have another rising edge. So with this rising edge, the program counter should increment from 0, 0 to 0, 1. Control T, as expected. So now we have a falling edge. This falling edge is significant because at this particular falling edge, we are going to combine what is inside the instruction register, which is 6C, with the least significant 4 bits of 0, so that we are updating the microcode pointer to 6C0. So this step is important and has a special name. Does anyone remember the name of this particular phase of executing an instruction? Yes. It's decode. Very good. Okay. So I am going to quote unquote take notes and say, what is the decode cycle? Okay, the decode is when the microcode pointer is 001, we have a falling edge, and the effect is the microcode pointer becomes the instruction register left shifted by 4 bits. That's one way to put it. Is that okay? Because the less than symbol is the left shift operator. So on one side you have a bit pattern, on the left-hand side you have a bit pattern that's going to be shifted, and then on the right-hand side it is specifying how many bits we are shifting to the right-hand side. So you're always shifting a 0 to the right-hand side, and everything else is going to move to the left-hand side by the number of positions you've specified.
And why do we do that?
The reason why we are doing that is because the microcode pointer needs to point to the location in ROM that contains the bit pattern that dictates what LDI is supposed to do. And the locations in ROM, at least in this particular processor, I allocated 16 locations for each opcode, and 16, in base 16 is 10. And that's kind of why. Does that make any sense?
Not.
Okay, so if we look into the content of the ROM, okay, it's a big mess like this. Each row has 16 items. So this is corresponding to the fetch cycle, or otherwise known as the no-op instruction. This one here this entire row is corresponding to the halt instruction. This entire row is not used. So we have a whole bunch of stuff that is not used. But if you go to row 6, C0, which is right here, this entire row is reserved to specify what the LDI-A instruction is going to do. Now, you see a lot of zeros because I over-allocated. I could have just allocated 2 locations for each opcode and I'll be fine because I have only been using RISC instructions, reduced instruction set computer instructions. So I just completely over allocated, okay? I'm wasting 14 locations out of the 16. But this is the reason why I need to um, do the right shift by 4, because the opcode needs to be multiplied by 16 to get to the right place in ROM in order for me to find the bit pattern to specify what the um, the rest of the processor is supposed to do. Is that okay?
Not entirely, but
Not entirely.
I'll go with it.
Okay. All right. Um, but the okay. So the important part is this is where we want the microcode pointer to point to, because this particular bit pattern dictates what the LDI instruction is going to do. So if I just kind of get rid of this for now and do another control T, that's the decode cycle. So control T right here, and we can see how the microcode pointer becomes 6C0, and then at location 6C0, we have this pattern of 1D80016, which by itself is not very meaningful. So what we'll do instead, we're going to look into all the major components of the processor. Did I highlight the major components of the processor in this class? I thought I did, okay, but I can do it again. So I'm gonna switch to Zernal and just do some highlighting here. So I'm using the highlighting tool already, and I can disable this tool over here. All right, so let me just go ahead and highlight the most important components. RAM is definitely one of those. The register bank is one. The program counter is one. The ALU is one. The flags register is one, but we are not going to touch it for some time. So right now, it is not of you know major concern to us. And I'm not even going to bother to highlight the instruction register, because the instruction register is only going to be updated during the fetch cycle. Okay, so nobody else, no other time, we are going to use the instruction register. So these 4 or 5 are the major components. When we need to figure out what an instruction is doing, these are the 5 that we need to keep track of. Are we good so far? All right. So now we switch back to Logisim again. So we ask the question. Okay, we go to the RAM component and we ask, are you being used, in this particular um, execution of the opcode? In other words, we are now executing the instruction. So there are 3 stages to the execution of the instruction. Fetch is one, decode is one, execute is the last one. We now know what to do with the opcode. So according to this, the RAM component is selected because chip select is a 1, which means RAM is paying attention. Then we have to ask the next question, which is, are we reading or writing? LD being a 1 means we are reading. And then we have 2 additional questions to ask. One is, who is telling RAM where to go? And then the other one is, who is getting the content of the location that we are addressing at this point? So those are the 2 additional questions. We'll address the first one first, which is who is driving the address port. So we track down this node. It ends with a multiplexer. So we now look at the configuration of the multiplexer. It has a 1 as a select, which means input 1 connects to the output. Then we track down input 1, and it goes all the way back to the program counter. So we know the program counter is um, connected to the A port of RAM, which means 0, 1 from the program counter is telling RAM where we need to access, which is 2, 4, which is the constant that we want to put into register A. So now the next question is, who is paying attention to the D port of RAM? Because RAM is screaming at the top of the lung of its lung and saying, I have this content of 2, 4 in hexadecimal or 00100100 in binary. But the question is, who's paying attention? I mean, if RAM is screaming this value out, we would certainly hope that somebody's paying attention and doing something with it, right? So now we track down this node, and we go to all the usual suspects. One of the usual suspects is the instruction register, but as I said a little bit earlier, the instruction register is typically not used, other than the fetch cycle, and it's not enabled, so it's not one of those things that we need to track down or pay attention to. This is a demultiplexer, or the output, one of the outputs of a demultiplexer. Fortunately, the demultiplexer is disabled, because we do not want the demultiplexer to have a screaming contest with the RAM component. So that's good. So now we go all the way to the left-hand side. This particular multiplexer is already disabled, so we don't have to track this down. And now we have this go, oh, wait, hold on a second here. Okay, I just misspoke. This multiplexer is not disabled because you can see the enable line is a 1 and RIMUX is a 0, which means input 0 connects to the output of the multiplexer. Are we doing okay so far? All right. And the register bank is receiving this particular content, which is what we know as 24 in hexadecimal or 36 in decimal. So we better go into the the register bank, and find out what is going on inside the register bank. So now we go in and we figure out that, hey, register A has enable being a 1 because it's output 0 from the decoder, and the decoder has a select of 0, 0, which basically means output 0 is selected, and whatever output is selected has a 1, and everybody else gets zeros. That's the behavior of a decoder. In other words, a decoder is basically like a demultiplexer, except the input is a constant of 1. All right. And then we look at the D port, because if A is enabled, if register A is enabled, then on the rising edge, it's going to update itself. So we want to find out what is happening with register A. So the input to the D port, or the value of the D port, is exactly 24 in hexadecimal, or the 36 that we specified earlier with the LDI instruction. So what is the rising edge going to do in this particular picture?
Okay, put that value into A.
Yep, exactly. So it's exactly as I said, right? We are going to copy 36, which is 24 in hexadecimal, into register A. So you might say, woohoo, we are done. No, not quite, okay? Because there's one little thing that is also important to do. So the little thing that is also important to do is the program counter. Because you can see the program counter also has its enable being a 1, which means the program counter is also about to update. The question is, how is it going to update itself? Can somebody answer that question? How is the program counter going to update itself? Just by looking at the colors of the wires, we should be able to figure that out. It's getting it from the adder. Okay, very good. So we can see how the D port of the program counter is coming from the multiplexer. The multiplexer has a select of dark green, which is a 0, which means input 0 connects to the output of the multiplexer. Input 0, in return, is the output of the adder. The adder takes the program counter as one of the input. It also takes carry in as the other input. So we are adding 1 right now. So the program counter is also going to be auto-incremented in this particular step. So that's why we have a post increment of the program counter. Is that okay? Because I want to bring everything back to the description in the browser. Let me see, where's my browser? Oh, it's right here. So I want to go back to the opcode description, and you can see how the PC++ is a post increment, which means we are dereferencing using what the program counter currently has. But after that, the program counter would also increment itself so that it is now 1 value, or at 1 more than what it used to be. Is that okay? Does anyone think that this is not going to work because you're pulling the rug under yourself? Okay, let me describe the process, why I think some people may have that question. Because the program counter connects to the A port of RAM. The A port of RAM, specifies which location of RAM to read. That thing, the content at that location is going to update register A. At the same time, the program counter is going to update itself by incrementing. So, some people may say, but this is bad because, when the program counter updates itself, then we're going to change which location of RAM we're addressing. And as a result, a different location of RAM is going to be selected, and then the output of that or the content of that location is going to be used to update register A. So, is that going to work? Yes, go ahead.
Isn't there a delay of some sort, maybe from the
Exactly. Yep. So, Rachel, you're correct. Okay, you're 100% correct. There's a delay. We are exploiting that delay. RAM is actually a very slow device. Okay, in real world, it is very slow. If you wanted to update to the next location, it's going to say, "Go get some tea going." Okay, I'll be done when I'm. It will be a while before I'm done. Okay, because if you have installed RAM, on a PC, and you have tried to push the performance of your computer, there are wait states. Okay, when you purchase RAM, there are wait states associated with all the operations of RAM. And guess what wait states are? Wait states are exactly what the name implies. It is basically telling the processor and say, let's say the wait state is like 4, okay? So it's telling the processor, go clap your hand 4 times, and when after that, the content of where you want me to present is going to be available. So RAM is a very, very slow component. Registers, on the other hand, is like bing, instantaneous. So that means, RAM in this case cannot possibly react fast enough to cause any problems. And besides, the rising edge is simultaneous. So register A and the program counter, they instantly get that rising edge to update at exactly the same time. So even RAM is kind of fast, it will still not be able to keep up with that rising edge. Is that okay? Because that is why we can perform. That's why we can document LDI as an instruction to be something like this. So that explains the mechanism. Now we ask the question of why are we incrementing the program counter again? So you have to think about, have we done something useful with what the program counter is currently pointing to so that we can now increment to the next location? That would be the question.
I would say yes.
You would say yes, yep, and the answer is correct. Okay, you're correct. The answer is yes, indeed, because on the rising edge. Okay, so let me go ahead and perform the rising edge. On the rising edge, you'll be able to see 2 4 to be reflected here, which means your register A should now become 0 0 1 0 0 1 0 0. And then the program counter would continue to point to the next location, which is 02. Now, this part is really important because if we did not do this, if the program counter is not incremented, then the next fetch cycle will mistakenly use location 01 in RAM as if it is an opcode, which would be incorrect because 01 is not an opcode. It is simply a value that we want to copy to a register. Is that is that okay? Are we doing okay so far with that concept? Okay. All right. So now we are ready for a falling edge. So with the falling edge, the microcode pointer should go to location 6C1, and it will, except we cannot see it. Okay, because at location 6C1, it has 2 followed by 6 zeros, which means bit 25 is the only one that is a 1 and everything else is a 0. So why is that important? Because bit 25 coming out of the D port, which is this Y over here, it goes to an OR gate, which means the output is going to be a 1 if any one of the input is a 1, and that goes into the reset of the microcode pointer. And that's why when we quote unquote increment the microcode pointer to 6C1, it will instantaneously reset itself back to 0. All right? So I'm ready to do a control T, and you can see how the microcode pointer is going back to 000. And can someone tell me, I'm right at the beginning of which phase of executing an instruction? Which cycle are we at? Hmm?
The fetch cycle?
The fetch cycle, very good. And what does it do? What does the fetch cycle do?
It's gonna read the location.
It's going to read an opcode from RAM and store that into the instruction register so that the decode cycle can use the instruction register to point to the new location in ROM so that we can then execute the instruction, right? So this is the beginning of the execution of the halt instruction. The halt instruction is not very exciting, as the name implies. So if I just kind of fast forward the control T a little bit, so you can see how the instruction register, I just completed the fetch cycle. The instruction register now has 01, which is the opcode of halt. This is a um, falling edge, and the microcode pointer is updated to 001, and then the program counter is going to update to 03. It's 02 right now, so the program counter does increment to 03, although we don't have any specified instruction over there. And now we have a falling edge, which means we're decoding. So since the instruction itself or the opcode is 01, when we decode it, it becomes 010 as we store that into the microcode pointer, like so. And the location 010 is basically they're all zeros. So the question is, did I explain in this class how the halt instruction does what it's supposed to do, which is halting and not do anything? I don't think I have explained that. So let me do that now. All right, so according to how the processor is configured at this point, the next rising edge, what is going to happen? Look at all of these zeros. Do you think RAM or any of the registers or anything within the register bank or the ALU will be enabled in this particular cycle? Nope, nobody else, right? Well, if nobody else is paying attention, so that means the rising edge is not going to do a single thing because RAM is not paying attention. None of the registers is paying attention. The ALU is not paying attention. So the rest of the process is like, whatever, right? So the rising edge is doing absolutely nothing, okay? Nothing in the processor is doing anything. But the falling edge is always going to do something about the microcode pointer because the microcode pointer's enable is constant is connected to 1, which means it's constantly on. But what is going to happen in this case? Okay, we know the microcode pointer is going to get updated, but how is it going to be updated? The color coding of the wires would explain that. The multiplexer that feeds the microcode pointer has a select of 0, which means input 0 of the multiplexer is going to be used to update the microcode pointer. The multiplexer, input 0 of the multiplexer, is getting the least significant 4 bits as a constant of 0. The most significant 8 bits come from the instruction register. Did we get something new into the instruction register? We have not, okay? It's still containing the opcode of the halt instruction. In other words, we're decoding again, but what are we decoding? The same instruction that we just decoded. So basically it is stuck in decoding. It keeps decoding the same thing. So do you think it's going to do anything differently? No. Nope. And it's stuck. We are not moving on, because the program counter is not incrementing, and we are just stuck decoding whatever is currently in the instruction register, which is the opcode of the halt instruction. And so this is basically mechanically speaking, this is how the halt instruction gets its quote-unquote job done. It has a very strange job, right? Your job is not to proceed any further, just get stuck here. Are we doing okay so far with this particular explanation? All right. So with that all said and done, I think I'm gonna take roll because I want to find out, who's here and who is not, particularly who's not. So we'll go ahead and take roll. If you use your mobile device or your computer or laptop or whatever to sign into Canvas, and I'm gonna pick out one of these things, to take roll. I think this one is a good one. So I'll change the date, obviously. Um, Originally, I was intending to take roll on the 17th, but I did not. So we're going to head and change that to the 26th. I think this one is already set up to use dmux as the access code. And let me just check the question, make sure it's, just saying, am I present in class today? Yep. Okay, so we are good there. And then we'll go back and set up a due date. Let's see, we have until what, noontime, right? Yeah, I think we got until noontime for the lecture. So I'll give you guys all the way up to 11:50 a.m. to do this part. Save and publish. There we go. All right, so you guys should be able to refresh and find the road taking activity for today. The key, once again, is dmux. Let me write it on the whiteboard, or I can do it on the whiteboard is probably better. Dmux. Demultiplexer.
Sorry, I was yawning with Pilates today.
That's okay. I know it's a Wednesday. Yep.
So when it halts,
Mhm.
let's say on your on on RAM you have some instructions that you want to fetch, but does halt like purposely do that for what? Just so it doesn't speed up or it doesn't? What does it do exactly?
Well, halt, because without the halt instruction, your program will continue onto the next instruction, onto the next location, the next location. What if you're really done? What if there's nothing else to do? You can write a tight loop in place of a halt. You can write a tight loop. In a real computer, in a real computer architecture, the halt instruction can also trigger power saving features. So it can basically power down a lot of the circuitry of the processor and even stopping the clock. So that way, if you're dealing with an MCU or what we call a microcontroller unit, it will basically be consuming like next to nothing in terms of energy. And that's what these fitness watches can that's why it can last like 4 or 5 days on one single charge, even though the battery is really small, is because most of the time it's sleeping. It will wake up periodically to check on things, and then it goes back to sleep. And the so-called sleep typically is a halt instruction, on the path of execution. Mm-hmm.
I'm guessing the halt, right, the output halt pin, that's all the way on the right there.
Yep.
That's just a reflection of when it is in halt, right?
Yeah, so if you look at the halt pin here, the output pin halt, it's the output of a comparator. This is what we call a comparator. So the comparator has two inputs. One input is coming straight from the D port of ROM, and then the other input is just a constant of all zeros. So it's basically asking, is the D port all zeros? If that is the case, if it equals, then the output pin corresponding to equal to is going to light up as a 1, and that's how we can tell whether it has halted or not. The halt pin is not really for your benefit as a person. It's more like for the benefit of the command line use of Logisim, because otherwise Logisim you're running on the command line would not know when to exit. It would just keep running and keep simulating. So the halt instruction doesn't do us any good to tell Logisim, hey, the program has concluded. Let's get out of here, right? But having this halt pin is important because the command line version or the command line way of running Logisim does look for an output pin called halt. And when that becomes 1, then the command line way of running logisim would exit. So this pin is mostly for that purpose. All right. So are we good so far?
And just
Yeah, go ahead.
that output pin,
Mhm.
it's all zeros when it has no further instructions in the ROM, right? Like, so there's no more instructions.
Not so much there are no more instructions.
Mhm.
It's basically just stuck.
Okay.
It's stuck in a way that it cannot execute the instruction of any other locations anymore. So you can have instructions after the halt instruction,
Mhm.
except you can't get there. You will not be able to get there because the halt once you get into the halt instruction,
Yeah.
you're stuck. It cannot proceed any further.
Gotcha. It's getting the same. The microprocessor is getting the same instruction.
It's not so much getting the instruction, it's decoding the same opcode over and over again. Yeah, it doesn't even go to RAM to try to get anything new. Yep, go ahead.
So when you write code, and say you're writing code and you have a return statement in the middle of your code, and then you have unreachable code at the end, does the compiler basically read your entire instruction set into the what you call it, into the RAM, and then that return statement or break statement, is that basically the halt instruction?
The halt instruction, okay, the best way to describe the halt instruction, let me see if I use that way to describe it in the opcode table. It's basically the forever loop. So the halt instruction, yep, that's 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 the equivalence of describing the halt instruction. It's basically a forever loop. You cannot get out of it. Yep. And no op, interestingly, is just doing nothing. So if you have a block in C and C or C++, open and close brace, it's called a block statement. But if you don't have anything within the block statement, it is still a statement, except it doesn't do anything. But it's not stuck forever either. Okay, so the biggest difference between a no op and a halt is a no op is simply taking up space. You can quote unquote execute a no op instruction, but then it moves on to the next location. So no op is not a forever loop. It is simply wasting, 2 cycles of execution and go like, I'm doing absolutely nothing, but the program counter continues to move on to the next one. Whereas the halt instruction says, this is it, okay? I'm not going to do anything any further. Is that okay? All right. So, questions? Yep.
So what would be like the benefit of using like the no-op one?
There's no, the no op is a free instruction. Okay, let me describe why it is a free instruction. So let's say, I can demonstrate it best using Logisim. So let me go ahead and reset the whole thing. So I go to here, reset, and you can see how RAM is all getting zeros, right? So let's go ahead and execute the program that is in RAM at this point, okay? We'll do it the quick way, and then we'll do it the slow way, okay? So let's do it the quick way first, but I need to lower the clock frequency so that you can actually see the visual effect. I think 32 hertz would be good for that purpose. So I'm going to type Control K right now to enable, and your attention can be diverted to the RAM component, and basically look at which location is highlighted. So here we go. What is it doing? It just keeps going, right? And the reason why it keeps going is because no op says, I'm not doing anything. I'm just moving on to the next instruction. It does not affect any registers other than the program counter and the instruction register, but none of the 4 software accessible registers, A, B, C, or D, is getting affected. So the question is, why does it do that? So let's go ahead and stop this, reset the processor, and try to execute it. Okay, so now we are back to the very beginning of executing an instruction, which is the fetch cycle, right? The fetch cycle starts at location 000 in ROM. Okay, we're all good there, right? we are going to fetch, which means the instruction register is going to be the content at the location that the program counter is pointing to. And what do you think that is? What is the opcode that we are about to read from RAM? 00. Very good. Okay, so let me just gonna kind of zoom out a little bit because I think it might be helpful to be able to watch a few things at the same time. All right, so I'm gonna put this all the way to the edge over here. I think this is good because now we can see the program counter, we can see the instruction register, and also the microcode pointer. So we just did a fetch. Um, the microcode pointer will increment to 001. Oops. There we go. And then on the rising edge, the program counter would increment to 01. Okay, there we go. And now we are ready to decode. And what do you think the decode is going to do? Remember, what decode does is to take whatever the instruction register has, left shift it 4 times, and then put that value back into the microcode pointer. So what do you think is going to be the new value of the microcode pointer this time? Hmm? What?
002.
No.
Micro pointer.
The microcode pointer, yes.
And we're at 001 right now.
We're at 001 right now, but we are at the decode portion of executing an instruction. Okay, let me describe what decode is going to do. It's going to update the microcode pointer so it becomes the instruction register's value left shifted 4 times. So what is in the instruction register right now, which is the opcode that we just fetched from RAM?
0.
00, right? What happens when you left shift 00 4 times? 000, 3 zeros, and that's going to be the new value of the microcode pointer.
So it goes down to 0.
Yes, it goes back down to 0, which, okay, so let's do that. Thing like that. So this is, now we are quote unquote executing the no op instruction. But where are we back at? Which cycle of instruction execution are we at?
Fetch.
The fetch cycle. And it's now trying to fetch the next location, which is 01. But what is the opcode at 01? You can see it from the screen. 00, which is the no op instruction. So that's what it does. It is quote unquote stuck. Well, I wouldn't say it's stuck, but the opcode of no op, which is 00, is really just specifying fetch the next instruction. So that's why it doesn't do a single thing, because it's just going like, okay, I get to this location, fetch the opcode, which is 00, put it into the instruction register, and then we decode the instruction register, which puts us back to the same place that we started off with one exception. The program counter is incremented. So we do move forward with the no op instruction, even though the no op instruction doesn't do a single thing, we do move forward. Is that okay? So it's not exactly a wasted opcode per se, it is a free opcode, more like. So the decode, the fetch and the decode still works, with the no op instruction. It's just that it doesn't accomplish anything particularly useful. Is that okay? I mean, does everybody understand why no op is not really an instruction? It is just another way to get back to the fetch cycle. Is that okay? All right. So for those of you who like hacking, the no op instruction is what you can use to make what we call a slide in exploits. So if you look into Stack Overflow or memory overflow kind of thing, if you can inject specific bytes into the stack or into some controlled portion of memory, you can potentially have a payload of doing something nasty, but you have no idea exactly where to put the payload. So what you do is you construct a slide to the payload. So that way, if you have some control over of the execution path and it lands anywhere on the slide, it will automatically slide down to the actual payload of the nasty malware. And that's a very well-known technique of Stack Overflow exploits. And the favorite slide is to use no ops. You basically inject a bunch of zeros into some region of memory. At the end of that slide, you put the payload code, and then you have another mechanism to control the behavior of the program so that it would land somewhere along the slide. It's hard to land exactly at one spot of the slide, and that's why we need a long slide to be the landing pad. But if you can land anywhere along the slide, execution will continue because, as you saw already, the no instruction doesn't do a single thing except to move on. So now you can slide all the way down to the payload of the code, and now the malware can now get its thing done, once it gets to the payload. So I just taught you guys, a little bit about,
How to make malware.
yeah, it's actually pretty hardcore, type of hacking that we are talking about here. All right. So with all of that said, we're going to talk about, other features of the assembler. So let me switch back to this particular slide. We go back to the assembler. And also we want to go to no op first. Okay, we'll do it this way. Okay. So let's say that we want to increment the value at a certain location. Okay, so the purpose of this program is to increment the value at a certain location by 1, and then we are done. Okay, so you probably will figure out that somewhere we need the increment instruction. So let me go back to the text editor to do all the text editing, and then we can get back to the spreadsheet. So we know somewhere we have to do an increment, okay, because we are supposed to increment the value of a location in memory. Except the instruction increment does not work on memory locations. The only thing you can increment is one of the 4 registers. Okay, so if you need to increment the value at a location of memory, you need to somehow get that the content of the location into a register first. So you need an LD instruction for that. So you need some kind of LDA and then some register B, because this is basically what is doing what this particular C instruction, this C statement is going to do, which is dereferencing B, treating the value of B as an address, go to the location that B is pointing to, grab that value, and then put it into register A. Are we doing okay so far with this notation? This is a basic C notation. And the next instruction here is basically the same thing as A gets A plus 1, which is pretty simple. And then we need a store instruction, which is the reverse of a load, which means this time we are copying the value of A back to where register B is pointing to. Is that okay? So with this, the first thing you probably need to do is to say, don't we need to initialize register B first to point to the byte that we want to increment, right? Because otherwise B is uninitialized. It probably just has 0 in it. So I'm going to do LDI here, B with some location. Okay, so I'm just going to say some location. All right, and this is the entire program. I put a halt instruction here. Okay, so I got a few problems here. The first problem is, which byte should I use as quote unquote a counter? Meaning, the location that I'm going to increment. Which location? I cannot use the locations corresponding to the program itself, can I? Because otherwise, I'll be destroying the opcodes themselves. That would not be good. Does that make sense? So, what is the? Yeah, go ahead.
Do you have to create an I, like a quote-unquote I in this
Well,
concept?
I'm trying to figure out what I need to use, or what value I should use to initialize register B. The question is where in memory, what is the first byte available for me to use as a counter?
0, 0.
Well, it's not a good idea, even though quote unquote we can do it here, but it's not a good idea because 0, 0 is corresponding to the opcode of the LDI instruction. You'll be destroying the instruction itself. So not a good idea. The next byte is whatever this thing is, also not a good idea. The next byte is the LDAD instruction, not a good idea. The next byte is the increment instruction, not a good idea. The next location is the store instruction, not a good idea. The next location is the halt instruction, not a good idea. The next location, yes, we can do that.
Oh.
So, do you want to do the counting? Well, let's first do the counting ourselves, okay? The LD instruction is the only one that takes up 2 bytes. So we have byte 0, byte 1 being used. The LD is going to be using byte 2, byte 3, byte 4, byte 5. This is byte number 6. Are we good so far? So after all that counting, I can now go back here and say, yeah, we can use location 6 here. So location 6 is going to be my counter. Yep.
What about situations where it's going to be like 400 lines long, you know?
Well, the problem is not that it's 400 lines long. The problem is, what if I want to add a new line somewhere within the 400 lines? Then everything is shifted after that one thing that you just added, right?
Right.
Then you have to do all the counting again. Would you want to do that? Would you want the tool to do that for you?
Yes.
That's what labels are for, okay? Labels are symbolic names of locations of things in memory. So we can do it this way, okay? So I'm going to write this program as just the way it is, okay? Copy and paste. You can paste over existing code, by the way, okay? So we can do something like this. Wait for it to assemble. Everything is good, right? And we can go to the assemble tab and see if, well, actually we can actually, because we can see how 05 as a location is the location of the halt instruction, which means 06 is indeed the first location that is available for me to use it as a counter. Is that okay? But the moment I do anything, like if, okay, so let me just do, I can't do that here, but I can do it in the editor. So if I just insert, some useless, no up here, that would shift everything, wouldn't it? Because now the next location, the location where the counter is supposed to go, is now location 7, not location 6 anymore. So the question is, how do I make the computer or the assembler to do all the counting so I don't have to? Is the concept of a label, okay? So the way to do this is to put a label here. The name of a label can be anything that is legitimate as a variable name in C and C++, or any identifier, okay? It doesn't even have to be a variable, it can be a function and whatnot. So it's basically any identifier in C can serve as a label name in the assembler. It is case insensitive, by the way. So I'm just going to say this is label 1, and the way you define a label is to spell out the name of the label, and it has to be the first thing on the line, and then use a colon to end the name. The colon is what is telling the assembler that I am defining a label. It is here. All right? So label 1 is going to be location 6 now. So once we have the label defined, I can refer to it. So I can now refer to the very same label that is labeling the first byte that is available as a counter. Are we doing okay so far with this?
By counter, you mean counting the...
I mean the counter, it's the location in RAM that I'm incrementing. Now this is not a loop yet, so it's not exactly critical counting. It's just incrementing the value of a certain location in memory. But it does kind of have the use as a counter because we are counting up by 1 in this code. Are we doing okay so far with this? With the concept of a label, how we can say, hey, it's basically a bookmark. Okay, I'm sticking a bookmark on this page. So now you can insert additional pages before that bookmark. It doesn't matter because the rest of the book is not stating the exact page number. It's stating the bookmark, the name of the bookmark. Is that okay? All right. So what we'll do is we are now going to copy this program over into the assembler, and we'll just run it. Okay. So now we have this new code, and if the label is mismatched, you will get an error message. In other words, if I misspell this name here, and let's just say that I forgot to put an E in label, like so, it's going to complain. It's going to say unresolved reference label LABL1. Okay, so that's an error message that is indicative that somehow this name is not defined anywhere as a label. So let me go fix that. There we go. And the assembler is happy again. We go to the RAM file and then we download the CSV. And this time I'm going to call this counter.csv. Switch back to Logisim. Reset the whole thing. Control R resets the whole thing. Getting the shortcut keys can be helpful. It's not like super helpful, but it does shave a few seconds every time you use it. We go to load image, and this time it is counter.csv. And we'll just fast forward to execute this entire program with our focus on location 06. This is our location. This is the place where it's going to increment by 1. Okay, so I'm going to go to simulate and enable ticking. Ding, we're done. Cool. Now, so let me pause the program and get back to the source code in the text editor. So what if you don't want to start counting from 0 for some strange reason? What if you want to have an initialized global variable that starts with, I don't know, 35? So that means somehow I need to specify, 35 in hexadecimal or in binary at this location. And that is the job of the byte directive. So when you say byte 35, what the assembler is going to do is to say, okay, I will just make the next byte location to represent the value of 35, which is 23 in hexadecimal, because it is 2 times 16, which is 32, plus 3, we get 35. So 23 is going to be the hexadecimal value at the same location, which is location 6. Is that okay? So at this point, I'm going to copy and paste the code into the assembler. But this time, in addition to running the code, we are going to take a look at the assemble view of the whole thing, because the assemble view is very helpful if you want to understand how a program is represented. Okay, so that's the only difference. We are starting with the value of 35, and it should end up with a value of 36 or 24 in hexadecimal. So when you go to the Assemble tab, this is what it looks like. It looks a little bit odd, doesn't it? Because it says, okay, if you look at column W says at location 06, we have a value of 23. That's what the byte directive is doing, is simply to say, oh, if you are just telling me that this byte location should have this particular value, sure, I'll make that happen. Is that okay? Are we good? All right. So we're going to do the same thing here, which is going to the RAM file. Once again, we download the CSV, and I'm going to call it the same thing, which is count or counter. Did I use counter or counter? Count. Counter. Okay. All right. So we'll replace it, and then we switch back to Logisim. Control R to reset the entire thing. Right-click on RAM, go to Load Image, specify the name of the file, which is counter.csv, and now we have the new program. So the new program versus the old one only has one change, which is the location 06. It was 00 before, now it is quote-unquote initialized to 23 to begin with. So now we'll execute the program again, Control K, And, oh, that is not good. Oh, it is good. It's fine because it changes to 20 to 24 in hexadecimal, which is 36. I just did not expect it to scroll. So are we doing okay so far with the program that we just looked at here? All right. So this is the other thing you can do. This can also use it. This can also use label one. You go like, what? Well, I don't see why not, right? Because label one resolves to a particular value, which in this case is 6. So what this is doing is we want this location here to have a value of 6. Is that okay? Because label one basically resolves to just an integer. So anywhere you can put an integer, you can put a reference to label one. It is just an integer. There's nothing special about label one other than it is a symbolic name for a particular integer, and the assembler is responsible to figure it out. Is that okay? And you can also do fun stuff in terms of math in an expression. So in addition to just label one, you can say, I don't want just label one. I want label one plus 2. You can actually do that too. Except this is an infix notation. The assembler does not use infix notation. It uses postfix notation. So the postfix notation is going to look like this. So I'm going to describe what is postfix notation in just quickly here. So if you want to express a plus b times c, I'm not referring to registers. I'm just using a, b, and c as just general terms. And you want this entire thing to be divided by d. This is just an example. This expression has no particular meaning. I'm just using it as an example. Divided by 1 plus d. Okay. If this is what you want to do in infix notation, the postfix notation is going to be a, b, c times plus, and then d1 plus divide. Think of it as Yoda talk. If you say, what is a plus b, Yoda's going to say, what a, b plus is. The verb follows the objects. That's basically what it is. Tag through a ball. Tag ball through. The subject, the object, and then the verb. Same thing over here. So let's check out what this is doing. All right, so A is just a value, B is just a value, C is a value. So at this point, we got 3 values, quote unquote, on the stack, doing absolutely nothing with it, right? And then we encounter a verb called multiplication. The verb is going to say, I'm going to do a multiplication with the last 2 things that you mentioned. What was the last 2 things that we mentioned? B and C, right? So it's going to do the multiplication of B and C. What is it going to do with the result? What is it going to do with the product? The product is going to become one of the items that is still sitting on the stack. So when the multiplication is done, when this is all done, this entire thing becomes one single item on the stack, which is right after the A. So by the time we get to the plus, it's saying, okay, I'm supposed to get 2 things to add. What 2 things am I adding? The one thing that's right before the add turns out to be the product of B and C already at this point of time. And then the item that's before that, well, that was the original A. So this plus here is going to multiply A with the product of B and C. And when that is done, this entire thing, which is A plus in parentheses B times C, would be the only item in front of D. So we have 1 item in front of D, and then we have D, and then we have 1. So at this point, we have 3 items. So this particular plus is going to say, okay, give me 2 items to add. Well, the 2 items to add would be D1 So we'll have 1 plus D or D plus 1 in this case. And then we finally encounter the division. By the time we encounter the division, there will be two things on the stack. This entire thing is one thing, and then this entire thing is the other thing. So we perform the division using this as the numerator or the dividend, and using this part here as the divisor. So that's how postfix notation work. If anyone is asking, why would you want to use postfix? This looks really awful. Well, I have a counter question then. Why are we using infix? Why are we using infix notation where the operator is between the two things that it's supposed to operate on? Give me a good reason.
It looks nicer.
It looks nicer because we're used to it. We have been poisoned again by the school system. First, by using base 10 numbers instead of base 2 numbers. And now we have been poisoned by, using the infix notation instead of the postfix notation. The infix notation actually is much harder for a computer to parse, to understand, compared to a postfix notation. And somebody's going to already thinking, like, do people actually use your postfix notation anywhere? I mean, this is just something that TACU invented, just like the TTP thing, right? Well, as it turns out, the answer is a pretty definitive no. Postfix notation is used in industry, the computer industry, quite a bit. Starting with the XP computers from the probably 70s. So if you have an uncle, or a grandparent or a granduncle who worked as an engineer in the 70s or maybe even the 60s, 70s, 80s, and you ask, so does your calculator have parentheses? That older gentleman or older lady is going to say, no, we don't have parentheses. We don't need stinking parentheses because we use postfix notation. That's one thing that is nice about postfix notation is you don't need parentheses. Okay? And then you go like, okay, but TAC, we are living in the 2022 right now. Okay, we are not living in the 60s or the 70s anymore. I go like, okay, have you heard of PDF? Portable document format from Adobe. All the things that I'm pretty sure you have dealt with at least one PDF just today.
They use postfix in there as well.
Yes. So PDF turns out to be the descendant of PostScript. And PostScript, if you purchase printers, 5, 10 years ago, PostScript is a big thing because Windows can talk to a printer in using PostScript, and it's a very general language for a computer to tell a printer what to print. And can anyone guess? I'll give you one guess in this case. Why PostScript starts with post?
Because it comes at the end, like the operations.
Because it uses postfix notation.
What do you mean? Wait, what? What was the question?
Why does the name PostScript, which is a name of the language that a computer used to tell a printer what to print, what is the content that you want to print, why does it start with post? And the answer is postfix operation. So to draw a circle, in typical C notation, you'll say, oh, there's a subroutine called draw circle, and then I supply the center, x, y, and then the radius, which is r, to draw a real circle. In postfix notation, it is x, y, r, draw circle. You specify the parameters first, and then you tell the language what do you want to do with those things that you just gave me. So postfix notation is actually used in real life in PostScript, which later on became PDF. So can you guys believe that some people actually handcraft PDF? You can write a program to do that, okay? And there are very interesting ways to do that. and there are actually applications to do that. So let's just say that you are trying to make a particular shape, like making a grid or a circle, with radiating lines, in a very specific way. You can just write the entire PDF, using a program. You can use a C program, you can use a Node or JavaScript program. But the whole point is you can use a program to generate the specification of a PDF so that the PDF, when printed, will give you exactly this kind of shape at exactly the right location that you want it. So anyway, definitely has nothing to do with assembly language programming, um, but now the assembler can take on postfix notation, which will come in handy later on. Okay, so right now for this lab, it's not as useful. All right, so I guess it's time for you guys to get started with the lab. So let me get it released. And then I'll upload today's lecture because you might need to reference today's lecture when you're doing the lab. So today's lab is called LD, ST, and LDI, which are the three instructions that we saw a little bit earlier. So that's why, that is why I chose to talk about those instructions the way that I did. And all right, we'll specify to have the answers released by 1:30 p.m. Is the computer club meeting today?
Yes.
So people will be coming? Okay, that's fine. We'll be fine. There we go. The lab is released. You can get started, and I'll be here to answer questions. And I can stop the recorder.